So it's a pleasure to be here and celebrate Bala. So I was previously a postdoctoral fellow here at ICTS in the Ajith's group, and of course Bala has been a great source of leadership for us. So I'll give a somewhat outsider's view of nucleus in Nsbh simulations. I went a little bit on the side with the interpretation, but not particularly on the aspect of physics that's so important for these systems. So I've had nice comments from Tim Dietrich and also Wolfgang Kastan about this. So as you heard from Larry, you actually need lots more than just GR and lots more than just GR with perfect fluids if you want to have a complete description of Newton's law in Nsbh systems. So here's kind of a overview of telling you all the things you have to worry about with Newton's law on the page. So, you know, it has a crust with actual nuclear physics, matter physics in it. There's a lattice that's with a solid. We don't know exactly what's going on in the interior. That could be superfluids, the magnetic field, all sorts of things. Fortunately, if you want to look at the Nsbh part of vector waves, is the simulation of just GR in both fluid hydrodynamics are probably good enough, at least unless you go to very high signal-noise ratios, which you don't expect to see until very future detectors. And this is what is used to calibrate all calibrated Nsbh models. Of course, the merger, you need everything else. Something if you want to look at like counterparts. Neutrino counterparts. So first, some successes. So you heard of it from there. There are now these catalogs of mostly BNS systems, but SXS has a few Nsbh systems. And also, these early ones that are covering enough parameter space are accurate enough to be able to use to tune phenomenological models like you were hearing about. We used to talk about this phenomenon B model. So it's an intertidal model that was used for analysis of CO2 and but the other real models was used for this analysis, but this one was tuned to waveforms. And the other thing is that, of course, you now regularly have more physics in these waveforms than just GR hydrodynamics. So now on to, so you've seen a very brief overview of the successes, some challenges. So first off is resolution. So you generally do not run these simulations with the resolutions you would like. So the current state of the art is from the AI group and has a resolution of 63 meters. So there's about 270 grid points across one by a neutron star. You go away from accuracy about 0.1 radians over an Nsbh, about 200 radians. So this is pretty good, but this is kind of really the state of the art. They're now putting out more waveforms like this, but this is still pushing things. For post-merger, the record is even higher resolution. This is at to 12.5 meters. So you might say, well, one thing you might want really high accuracy for is if you wanted to try to say the difference between these metric log numbers, you can put with teleperturbation theory, and directly we have the waveform log numbers, which was the thing that you had comments from Gil about. This could be something that you could do a very high accuracy. So the alien progress would be something you could extract from it. So the other thing you might want to worry about is length. So say the art is for against the SXS, 22 orbits. That's for in spiral. Well, covering only, however, a little more than 100 milliseconds. Well, 3817 lasted for more than 100 seconds like a band. So there you heard these black hole simulations go to more than 100 orbits. For eccentric BNS resolutions with here instead of a spectral code, a difference code, you've had some ones that go a little longer, 117 milliseconds, and also people have done post-merger simulations, these ones a bit longer as well, given what they difference code. So just to kind of put this in perspective, here is actually this last 30 seconds of the chirp of 7817. Here's just where you'd have actually this little sliver is this SXS simulation. So the other things I'd worry about is when you're doing these hydrodynamic simulations, you do not have a sharp fluid to vacuum interface. You put in some low density atmosphere. People have been successful in lowering this still, but it still is a significant contributor to the air, particularly if you want to look at the ejecta, which is fairly low density itself, and it's going to travel up to all of this atmosphere that goes out towards the observer, or you would see where it will start forming better counterparts or kilonova. And of course, you have to figure out what is unbound. You want to know how much matter and what parts of the matter have unbound. So if there's a proximate method used to determine how the matter is bound, they don't agree with each other. So there's something else. What about maybe there's a possibility of interfacing with smooth particle hydrodynamics methods. So the other thing that people are now looking at is if you have large mass radius, people does like 2 to 1 mass ratio system, so large mass 2, small mass 1, and precession, again, which started to see if there's something more that we're going to look at in the future. The initial data, so unlike forward by black holes, where you regularly have conformably curved data, but I do start to use conformal practice. With low spins, probably not a problem. If you're pushing spins higher, you may want to drop this. It may not be necessary, but it may still use better initial data. Conformably curved initial data are used for still a high spin in black hole neutron star simulations. It also have to worry about the eccentricity. So here, neutron stars are lagging a bit behind where you can get for black holes. And remember, so eccentricity is around 10 minus 3, so it's a little below there. Whereas for black holes, you get out 10 minus 5, or using this case, that's 1, 10 minus 4. High unit for spins, so this is possibly something that you might not have astrophysically, but you want to be able to check what you do. So currently, Katishi and collaborators have got that to spins at an evolution of 0.52. And Fokai also has been working on getting high compactances, so reductions are close to the maximum mass. And then, so, it turns out that there's better initial guesses, and also the SXS group has been working on sim Nsbhs. But the simulations are not explained. So now going beyond just regular GeoHD, so if you want to include nuclear physics, so you usually have things that include thermal effects, chronologically. You can also be able to directly take what's something that the nuclear theory computer, which actually has both the effect density and pressure. So the pressure density is also a function of the composition, the electron fraction, and the temperature. So this is something you do. You also actually like to include the nuclear reactions themselves, and it's partly for the ejecta. So people do include weak interactions that will get neutrinos, but not the nuclear ejecta. Both guys will tell me he has some work that shows that this could be the importance of just post-processing what you get out. You have to track the neutrino during the simulation. Also, could worry about viscosity. This would also come from imaging turbulence, and there are various opposite ways of looking at this. Similarity is again something that nobody's looking at. Magnetic fields can affect lots of things in the post-proto. For instance, you would know when you form a hybridized neutron star collapse to a black hole, which you actually might see. You could see the post-proto wave signal, so you get a lot field, and of course, other things. So you can see the jet being formed from a group. So there are currently high resolution that can be understood. It's still not able to resolve the image in the spots movement. Currently, you add magnetic fields either to initial data by hand or something to the simulation. So clearly, these are not technically important, so it's okay to do this, but it's still nice to have consistent initial data. And you also use using ideal GeoHD. There's claim that this is okay as long as the UHD population itself is okay, but there are also some people using non-ideal images, so we can just neutrinos, you would like to solve the multiple equation for neutrino transport. But this is very, very expensive, so people use various approximations to it. These moment approximations from Thorne and Shirata et al. Collect the art. So Sathyaprakash, the SXS collaboration on this, and also testing this against a same transfer equipment. Find that it's maybe better than you might hope it would be, but it's still towards poles, but off by a factor of 2. So you want to have accurate treatments of the ejecta in particular, you'll need to have neutrinos include well. So something else that no one, as far as I know, is currently working on, that people have worked on a bit in the past, is if to include the elasticity of the crust, and possibly if you have exotica, like you had to work with phase, such as the solid quark star, the elasticity of the entire star, or the core as well. So this is something that could actually affect the rough numbers or tidal formability in the spiral. We all done Parameswaran theory calculations for the crust, and so it's affected by less than 1%, so it's probably not a huge deal, so this only affects the crust. However, if you have a solid star, it could be a factor of 2 different extremely extreme parameters. It's also, you could worry about crust cracking for much leading to really short EM signals, or even having disparate effects on crust crumbling that Gachanov talked about quite a while ago. So, 70 Erickson, you're talking Charles Pollock looked at this quite a while ago, but did not get very far, as I can tell. They had one paper about the formulation and some talks, but nothing more than this. So something else that kind of is to be in the back of what we're going to find between these situations is, can you say anything useful on this PG mode tidal instability? Here the idea is that you have a diurnal tide from the companion that couples to high order pairs of modes, so these P modes, other modes, and G modes, which are buoyancy modes. And so the difficulty here doing this, we all done LO calculations, but it said, well, this could be an effect, but no way actually telling with the calculator able to do currently. So we like to do a numerical simulation. They require extremely high resolution because you need very high order modes, like n equals 1,000. And also you have to simulate a non-barotropic fluid or to have the G modes because these comes in gradients. We are currently looking at from a total analysis of effect using 7817, but it would be nice to have some more theory to back this up. Finally, you might also want to do simulations beyond GR, not just with binary black holes, but also binary phase systems. Particularly, there are things like scalar tensor theory that you have binary black holes, exactly the same, but if you have binary neutron stars, you could have neutron black hole systems, you have some different. You will have done some digital simulation theory. I think this is something else to look at in the future. Also, if you have, say, these about having these hidden fields coupling to these the neutron stars, because else we don't simulate. To conclude, you need lots of physics if you want to describe all of neutron star and black hole systems. If you want to just describe the inspiral gravitational-waves, we can probably get away with just Pope fluid GIHD. But if you want to do anything with Berger and for even counterparts, you would probably need to have lots more expected fields, neutrinos, that sort of thing. So it's challenges even for the GIHD cases of the length of the simulation, the accuracy, and the grounded safe covered. And it's even more the case you add in more physics. So I think I'll leave it there.
With regard to GW 170817, it lasted hundreds plus seconds, it doesn't matter. Mm-hmm. You said the longest simulations are really nowhere near that, but how long a binary neutron star waveform do you think we need in order to incorporate tidal effects and not worry about systematics purely from the point of view of measuring neutron star radius? Is there an estimate of how long you need?
Yeah, I think luckily most of the tidal effects do come in in spirals, so you could have some hope that you're calibrating your calibrating your waveform model to numerical simulations, that just having the final bit is okay. But it'd be nicer to have something where you could have about a longer overlap with even Positonian waveforms. So I'd say at least you would like to have an order of magnitude more, because it's actually quite a lot.
Thank you.
Hi there. So this is regarding your comment about including nuclear reactions during the simulations. Do you think that the energetics will be important for the hydrodynamics? Because in general, supernovae also they are not so important, like for type 1 at least. Do you think that the energetics is so high that we have to include during the simulation?
I think the idea is not that they're important for the dynamics of the system, but they're important for the properties of the ejecta. You want to describe how the matter that was ejected depends on, say, the electron fraction, temperature, things like this. When people do these kilometer simulations, they'll take the ejecta from some simulation, run it through a nuclear reaction code, and ask what you get out at the end. But you may even need to start doing this early on in the simulation to track how the nuclear are going before the simulation finishes.
So thermodynamic history of the ejecta will change significantly. Okay.
So I have more of a high-level comment. It's of course much more difficult to get accurate results for binary neutron stars than for binary black holes. And I agree with Larry that quantitatively it's much worse than for binary black holes. But on the other hand, it's also that the physics is such that small changes in the initial parameter can make big differences in the outcome, in particular if it's things like ejecta or the lifetime of the remnant. So I think even if we could perfectly solve the whole problem, we might still not be able to trivially get constraints for certain things, because you still have a certain variation that is essentially unpredictable. In particular, if it's a low amount of ejecta, I think there's a lot of effects that might come into play that change very drastically if you change, for example, the initial masses or spins or even magnetic fields. So there are two sides to the problem. So it's not just that the methods are not up to the task, it's also that the physics is actually more complicated.
We can also have a question for all the speakers in this section as a discussion. Sukant.
So it's a follow-up on what Wolfgang just asked. The question is, so, we had some very useful exercises with Ninja years ago, almost a decade ago, which were helpful in using numerical relativity waveforms. It pinned our faith in what different groups were producing and then use them in their detections. How difficult is it to do, or does it even make sense to ask a question where we do similar things with binary neutron star waveforms, especially for the merger and post-merger parts, where let's say we have different codes from different groups, but we try to start with very similar, microphysics and initial conditions, and then evolve to see how different the waveforms are. Eventually, we aim to, detect the post-merger oscillation frequencies. Do these frequencies differ from one group's predictions compared to others?
So maybe I can comment on this. So I think the post-merger frequency should be fairly robust. So I'm not aware of a publication that does exactly what you just asked, but I was involved in an informal project comparing different codes with the same thing. That was mainly the Inspiral, which matched not as good as these binary black hole things, but good enough. But for the post-merger, I think the frequency is one of the more robust things also if you change physical parameters like spin and so on. So it's not that sensitive. It's other things like ejecta of mass, lifetime of the remnant and so on that are extremely sensitive, and I think there are the real problems. And since ejecta are coupled to kilonova, that's also an important thing. And don't even get me started on short gamma ray bursts, which we essentially don't know anything how they work. And yeah, then things like neutrino physics, of course, that is a very difficult thing because opacities for neutrinos depend strongly on temperature and the equation of state. So the slightest change could change the radiation coming out of the remnant, which might change the composition of ejecta. So this is, again, something that is physically complicated and not just numerically difficult. So even if you solve it exactly, you might still have the problem that you don't really know the initial conditions good enough.
No, you rightly pointed out that there is a lot of physics, and therefore it's not just about numerical simulations. But the problem is, if you take the same code and slightly different initial conditions, the final result seems to be very different sometimes. But is that really a physical thing, or is it something to do with codes? I'm asking you, yeah. Extreme sensitivities.
Okay, there are some things that should not be very sensitive, and others are, for example, the remnant lifetime. So if you have a hypermassive star, it's extremely close to collapse. It's a very fine balance that keeps it from collapsing. And if you change the mass a little bit, you need much less kick to actually make it collapse. So the lifetime can change from a millisecond to 50 seconds when you just change the mass by less than 1%. Okay, don't quote me on this number, but it's a very small.
That's an extreme example. I'm not talking about that. I'm really talking about those in which you start, instead of r equal to 10m, you start at r equal to 10.5 m, exactly the same physical system, it seems to then not give you the same answer. That's what I've seen in some simulations.
So you're talking about the initial separation where you start evolving.
Correct.
Yeah, okay, that's also something that might have an impact, because that depends then, that influences the eccentricity you get if you don't correct for that. So that is a distinction you have to make. If you don't correct for eccentricity, that should have a relatively large impact. So if you come very close together, you essentially evolve something very eccentric. But yeah, I agree, these things should be investigated. I'm just saying that even if we get them under control, it's still more difficult than the binary black hole case.
So you can keep this. No, please keep the mic, because it is a continuation of the same thing. Yeah. So I mean, what you're pointing out is that there is physics, which is all these things that we heard from the talks. I mean, neutrino transfer and equation of state. But there's also just the initial conditions. But are you saying that something about the physics of ejecta and so on will be degenerate between the choice of initial conditions and this physics of the parameters, I mean the physics of the system? Because if it is degenerate, then it's hopeless, right? Then we might as well just not do anything, because we would never be able to tell. Because if in fact I find something, right, and some ejecta with some properties, some lifetime of a hypernova and so on and so forth, and then I could not tell really if it was from there, I cannot really deduce anything about the equation of state, because she may have an equation of state and some initial condition and it reproduces it. And he may have another equation of state and some other initial conditions that reproduces the final observations. Is that what you're saying? That there is a potentially large degeneracy between initial conditions and the physics?
Yeah, that's a good question, but also very difficult to answer, because the kilonova is many, many levels removed from the initial conditions. So there are a lot of physics going on between the thing you can detect and the thing you put in. And it also depends on what exactly you're trying to model. So if it's just the overall luminosity or even the fact that there's a kilonova at all, you can already get some relatively robust constraints. So if, for example, you have prompt collapse, there will be almost no ejected matter, so probably no kilonova. So this kind of thing is robust. But if you then look at the detailed spectral evolution, that might, for example, depend on the lifetime of the remnant and the neutrino luminosity of the remnant. And this in turn could be related to magnetic effects, which we cannot model currently well because they are arbitrary small scale amplification effects. But also the initial data. I mean, we don't know anything about the initial magnetic field in these merging systems. So the more detailed you can measure the outcome, the harder it gets to model it accurately enough to get information out of it. But I think we do have a chance to get a lot of physics out that is robust enough to say something. Yeah, that's my opinion. So I might be wrong. I think it's really useful to get all these errors in numerics under control, but one should also have a look on the physics side. So how, even with a perfect simulation, what could we actually say?
This is to Prayush, I mean more to Prayush than others. Is there a strong motivation to include merger and ring down for, let's say, LISA data analysis?
Test of no-here theorem, for instance, would be one of the strongest motivation. If you really want to test gravity in the strongest regime, you need to test it around the time the two black holes are closest to each other.
So you
will have signal to noise ratio of several hundreds in just the merger ring down portion of the signal. So in other words, it's $1 billion experiment. We don't want to sacrifice on any science that can be extracted out of it. And that's why we need the merger ring down signal to be modeled very well.
But you can test the no-here theorem just based on the perturbation
that's
theory.
One example.
Okay. And another question, it's more related to modeling. So we have both the CIFOR and strain data available to us in various catalogs and so on. But which one is better suited for, let's say, a modeling kind of thing? Because I guess the strain data is extracted from the CIFOR data itself. So do we have an understanding which one would be better, let's say, for modeling purposes?
So there's a figure that shows the errors in both CIFOR and strain in the recent paper by SXS, which puts out the public catalog this year.
Thanks.
And those errors are very comparable for both.
Okay, so these are the errors in our simulation.
In the estimation of the final CIFOR and as well as for the edge.
Okay, but don't you get the strain from CIFOR? Okay. Okay, thanks.
Yeah.
Yes, I just wanted to add a comment to the previous question that you asked. So the example of the quasi-normal mode that Prayush was making, I think is important, but even more to get the mass correctly, and in particular the mass ratio, you need to have also the mergering down, because if you use just a spiral waveform, you will not be able to break the degeneracy, while the mergering down gives you the total mass. And so it's actually very important to have the mergering down for have enough to noise. Even before going to test OGR, we want to get the parameters right.
Right. And there's several reasons I can add to that. So for instance, just to be able to extract Emery physics, right? You need to be able to subtract out the several MB/HB signals that you have loudly present in your data. And if you leave out a lot of noise in terms of the merger part of that signal, then that can easily get confused with some harmonic or the other of Emery's, for instance. So you really need to subtract out. It's a subtraction problem. For that, you need the whole signal as accurately as possible.
Okay, this question is for all the three speakers of the session. There's another interesting source which will be particularly relevant for the coming from the core of the globular clusters, and that is to do with unbound systems of black hole and neutron star, where a neutron star initially in a hyperbolic orbit comes very close to the black hole and gets tidally disrupted. So as numerical relativity, looking at this source, the gravitational waves, when the neutron star is very close to the black hole, while passing by it gets tidally disrupted. But one would expect that there are many more such sources than bound eccentric systems.
I don't do any of this work myself, but there is some work on tidal disruption events. Okay. There are some people who are looking at tidal disruption events for these large hyperbolic type encounters. I don't do any of this work myself. This has only been just done within the last couple of years, as far as I'm aware. So I don't know of any concrete results that they've done, but I know some people are interested in looking at the problem.
Okay, one last question.
Yeah, so coming back to binary black holes and their utility for LISA observations. So I think, Larry, you showed this comparison among different waveforms from different groups. And yeah, for LIGO, I think those errors are very tolerable, but not for LISA. So how do we get rid of that discrepancy? Is it just a technical problem, or is there any conceptual aspect to it?
So for low mass ratio, it's just a matter of pushing the resolution of simulations, I would say. For a higher mass ratio systems, over 10 to 1, 30 to 1, so on, these type of simulations take current codes. Our current code would take several years to do, say, a 30 to 1 mass ratio for 40 orbits or so. So we're working on a new code that should be more parallel, give you higher parallelization to cut down the wall clock time of these simulations. But there are some issues, there's some technical issues when the small black hole, so we use excision in our simulations. And when you have a very small black hole next to a large black hole, you have to keep this excision region inside the horizon of the black hole in order to have well-posed system. And that becomes very, very challenging. So we'll probably need to develop new numerical techniques to handle these cases for LISA, I would say.
Okay, let us close the session with thanks to all the speakers and